Swayam Prabha. Digital India. Educated India.
Welcome all of you to these lectures on dimensional analysis. This very interesting lectures what today I will cover it, talking about how to do the experiments in fluid mechanics to characterize the flow behaviors. So, very interesting topic, and this topic I will cover it in two lectures. So, today lectures and the next lectures what I will cover it. Again I am following these three books which already we discussed earlier, the Senthil Simbala, F.M. White and Radhakrishnan. So, today I will start with a lot of good examples what we have carried and we discussed that. So, I will talk about dimensional group, dimensional homogeneity principles, Buckingham pi theorems, dimensional groups what used in the fluid flow. That is what I will introduce to you. Then we will discuss some example problems based on Buckingham pi theorems and we will have a summary. So, as I started earlier, let us start with very interesting examples what we observed in May 3rd, 2019. You can see this overturning, vast overturning in this, okay, because of the super cycloning what it happened in May 3rd, 2019, and this is what we conducted the experiment in wind tunnel at IIT Guwahati. The questions rise that, as you know it, this is a full scale models, okay, prototype, and this is a model. This is a full scale. That's what you got it in the cycloning storms and all. This is what I conducted in a wind tunnels, and we are getting the similar trend. Are they enough for a study to conduct, or we need to do some sort of a similarity analysis, the flow pattern analysis, how you do it, how do we design these experiments. This is what I am just demonstrating you. When you conduct the fluid flow experiments, you have to first design the experiment, how we do that. So, those things today I will discuss it. Before that, I am to just show you that there was a instrument which can measure the drag force measurements, experiment set up like this, where you can compute the pressure coefficients, and if you integrate it, you will get the drag coefficients, and that way when you have put a cylinders, you can compute the what could be the drag, the force acting on these cylinders with the varying the fluid flow, the air flow conditions here. So, these type of experiments is possible now, and we also have a facilities in Department of Mechanical Energy to visualize that how the drag force are hafting it. One case I showed you the wind tunnel lab, another case I have shown it that how you can measure the drag force measurement in IIT Guwahati setup what we have, where you can measure the drag force. Okay, as you know it, drag force is a very preliminary data for any experimental designing. So, drag force we use for this case, we are just talking about a drag force for a cylinder. Now, come to the dimensional groups. I think this what you know it even if at the class 11th or 12th levels. So, basic dimensions what we have: mass, length and time. These are three basic dimensions: mass, length and time. So, what we have when you do a theoretical analysis or the experimental analysis can be made universal. Okay, that's what is I am highlighting here. Independent of specific locations, using a dimensional group to express them. What I am talking is that we will discuss more in this. We conduct the experiment, but the experiment becomes universal when you make it a dimensional analysis group analysis. Otherwise, it will be a particular case studies, not the experiments what we are doing for inversional study. So, we have a very basic dimensions of any variables, that mass, length and the time. As you know it, what is the velocity? The distance per unit time, the length by time. So, any of the fluid flow variables we can define in terms of these three basic dimensions: mass, length and time. Now, if you look at the fluid properties what we have, some of the fluid properties is, you know it related to the dimensions. Okay. That's the length, area and the volume. So, it is just a dimension, geometric dimension. So, it has only unit in terms of the length. Okay. So, that means length is L1, L square and area will be L square, the volume will be L to the power 3. So, you can understand. What is the velocity? You know it, length per unit time. The accelerations, similar way you can know it. Let me look at what is the discharge or volumetric rate, the volume per unit time. That would be LQ divided by T, that is the volumetric. Then we have come to the two different part. One is kinematic viscosity, as we discussed in Newton's laws of viscosity, is that it is independent of mass. So, you can understand it, it has a dimensions of length and time. Similar way, the CA strain rate also independent of mass and length. So, if you look at these properties, all are independent to mass. First, I start from length, area, volume, then fluid properties like velocity, accelerations, volumetric rate or the discharge, kinematic viscosity and the CA strain rate. Now, if you look at other part like pressures, force per unit area, similarly trace force per unit area. So, force you know it, that will be the mass into accelerations, the force will be mass into accelerations. The pressure and trace will be the force per unit area, that is what you can compute it. Similar way you can compute the viscosity dimensions if you know very basic equations of Newton's laws of viscosity. If you just CA stress is a proportional to CA strain rate, the proportionality is the viscosity. So, you can compute it what could be the dimensions of the viscosity. Similar way, let us come to next levels with the momentum flux or the torque. So, that what will be have a this unit, the power, work and energy, you can find out what will be the unit. Then I am coming to the other two properties is specific weight and mass flux, mass per unit time, that is what is mass flux. Similar way, the surface tensions you can compute it, what will be the surface tension. So, that what is force per unit length, that is if you look at that, the force per unit length usually come into a surface tension. The density mass per unit volume. So, if you look at, if you know very basic the definitions of these fluid properties, you can easily write these properties in terms of dimensioning, in terms of mass, length and the time. So, it is very easy. If you are having any doubt about that, you take a equations, like you have a doubt about what could be the dimensions of viscosity. Then you write Newton's laws of viscosity, that is what the tau CA stress equal to mu dV by dy. Substitute the CA stress, what is the unit? dV by dy what is the unit, then you will get the mu, because this is a dimensionally homogeneous equations. So, what I am to talk about that, if you are just forgot that what could be the dimensions of a particular fluid properties, try to remember a dimensional homogeneous equations where that properties are involved. If it's you can get it that and substitute the dimensions of the properties like here this shear stress, the velocity gradient and the mu value, then you can get it what will be the dimensions of mu, and you know it what is the relationship between kinematic viscosity and the viscosity or the dynamic viscosity. So, if you know the basic relationship between the fluid properties, also we can compute it what will be the dimensions of the fluid properties. So, whenever you have the problems, first you write the dimensions of the fluid properties, and if you know the dimensions of fluid properties, then you can easily find out what could be its unit. Okay. In terms of kg per meter cube, what is the unit of that? That what you can meet it, mass will be in kg, length will be in meter or centimeters, and the time will be in second, hour, day, we can have a different time frames. So, it is a very easy task to make it a dimensions of the fluid mechanics properties. Let us go for the what is the principle of homogeneity. All the equations, not all the, so most of the equations in engineering, most of the equations of in engineering dimensional homogeneous, not all. That's let me have a repeat these things. That means what it indicates us that the dimensions of the equations will be the same. Okay. The left side of dimensions LHS should have the dimensions of right hand sides, then the equations are dimensionally homogeneous. So, that means what we have to look at that any physical properties and all, so somewhere it follows this dimensional homogeneous concept. Those are the concept we have to use it for designing the experiment. For example, if I compute a drag force like what we had in the experiment setup, what I showed it, that I have a cylinders, I am making a velocity v, and I try to know it what will be the drag force. Okay? If it is that conditions, if it's that is the conditions, if it is the velocity v, these the diameters of the cylinders and the drag force Fd I am looking at. So, other two properties also matters it, rho and the mu is the viscosity. So, it depends upon the viscosity, that means it depends upon whether you have in air or the water. So, its density varies, the viscosity varies. So, the drag force what is happening it is a functions of d is a diameter of the cylinder, v is the velocity of the flow, and the rho and the mu is the fluid properties related to density and the dynamic viscosities, the viscous force components. It depends upon the, like you can know it, the drag force in oil will be the different compared to drag force in air. So, that way the mu will take care of what type of drag force will be there. D also depends, if you have bigger diameter or smaller diameter, D also matters to power. So, the drag force is a functions which we do not know it. Okay. D is a functions of the diameters, V velocity of the flow and the density and dynamic viscosity. If it is that, now I have to design the experiment to finding out this F component. How we will do it? There is two ways to do. First is that I know it, what I can do it, since F is a functions with a 4 independent variables. I will do a 4 type of experiments. That means, when I am conducting an experiment between changing the D and different V1, V2, V3, I have the making a constants of rho and mu. Similar way, I will change the other parameters, keeping other parameters constants. See, if I am trying to do that, because how to try to get a functions on that, I will give it 2 parameters fixed and I will run for a series of experiment, let be a 10 experiment I will do it to get a curve. If it is that the conditions, that means for the 3 independent variables, I will do it 10 into 10 into 10 into 10. That is what will come out to be the 1000 experiment. So, if it is a 1000 experiment, then it is too expensive for us. But what we have to look at that, whether there is some sort of dimensional relationship is there between these independent variables and the dependent variable. If they have the dimensional relationship and that relationship we can get it, we need not to do this 1000 experiment. We can do less number of experiment. That means you can do a 10 experiment. If you do a dimensional analysis to design these experiments, you just do a 10 experiment to complete this process. What way to do it? We make a non-dimensional form. That f by rho v d squares, if you just substitute the dimensions, you will see that it does not have a dimension of this type. Rho v d by mu also does not have the dimensions. You just substitute it and try to find out rho v d by mu, which is very well known equations which called the Reynolds equations, okay, Reynolds numbers. Okay, we will discuss more that in pipe flow. And so, if you look at that, what I have developed now, instead of the f functions, we are looking at g functions, which is a relationship between 2 non-dimensional group. One is left side and the right side, they should have the same, and I will looking at different functions. If that is the conditions, I should conduct a relationship of experiment of different Reynolds numbers and can get it from the experiment what will be the force and non-dimensionalized as a f1 functions and draw it fit a functions, get it these data. So, only 10 experiment are enough for this study as compared to conducting the 1000 experiment. So, the non-dimensional experiments making us that we can make a dimensionless force plot and we can conduct the experiment with a different Reynolds numbers and plot, because once you do with a different Reynolds experiment, you will get the force, you know the velocity, you know the diameters of the cylinders, then you can compute it what will be the non-dimensional force component here, and if you get this curve, then it is easy to find out at different Reynolds number what will be the force. So, one is that this dimensionless analysis saves us doing a large number of experiment. Second is that when you put a non-dimensional forms, it is easy to interpret the data as compared to the doing the individual basis. So, the dimensionless plot and this analysis help us to save the large number of experiments, as well as this it help us to interpret data better way as compared to do individuals. Almost all the time any experimentalist, they start designing this experiment using dimensional analysis. It is not only the fluid mechanics, economic models, socio-economic models. If you talk about any experiment what you conducted it, we always do a dimensional analysis to find out the how many experiment we should conduct. Now, let us come at how to do that is Buckingham's pi theorems, which is very simple pi theorem concept is that. So, if you have a number of independent dimensional groups, how many number of independent dimensional groups I will get it. If there is a n dependent variables, okay, we know it basic dimensions are 3, mass, length and the time. So, that means we can group it, a non-dimensional number will be the n minus r. Please remember, as you know it, the dimensions should be 3, but not always be 3. Okay, that is again I am to highlight it. has to have a judgment for that. If you know that a particular dependent variables it is having these many of dependent variables. If you can visualize that what are the force component, what about the variables are going to play for that components, then you do a non-dimensional analysis to find out the relationship between dependent and independent variable. Now let us come to that same problems is a drag force on a sphere. Okay, it's easy now. Okay, same concept in a fluid streams, the same problems. Okay, you have a sphere here and you have the flow is coming here like a cricket balls. Okay, you are throwing the cricket balls. Okay, and you try to find out that what could be the drag force. Okay, what could be the drag force is acting on that, what will be the drag force is acting in that. See, if that is the conditions, I can visualize that it has a dependency of velocity, the dimensions of this, the diameter of the sphere, the fluid properties like mu and the rho. So, the total number of dependent and independent variables are 5, basic dimensions are 3. So, we can make 2 number of independent dimensionless groups. Is it correct? It's very easy things that we have to find out the dependent variables and the independent variables, count that, and we know the basic dimensions are the 3, mass, length and the time, and we just subtract it and find out that we can have a 2 number of independent dimensional group. Now, I have to develop the dimensional groups of that. So, if you look at that way, first what I have to do it, I have to write the dimensions of each one, force, mass into accelerations, the length, the velocity, density and the dynamics viscosity. If you do not remember the dynamics viscosity, the dimensions, please remember Newton's laws of viscosities. Okay, anyone you have to remember it. Okay. So, if you do not remember the dimensions of dynamic viscosity, please remember what? Newton's laws of viscosity. If you remember it, you can easily compute it what could be the mu dimensions. That is what always you confuse in any of the exam. That is I want to give you that in order to remember all the dimensions of the fluid properties, but if you know it, the basic equations, some of the basic equations, you can easily find out what could be the dimensions of the that dependent or independent variable. Now, if you look at that, this is called the phi theorems. Okay, it's a very easy concept that the please don't have a confuse with the pi means 3.14. That is not. It's a non-dimensional form of phi. Okay, so if it's that, I can have a 3 variables. Okay, that's the length, velocity, and the rho, and the force. These are called the repeating variables. Length, velocity and density, I will put a repeating velocity and with the f. Similar way, the length, velocity, rho will be the repeating variability and then I am substituting the mu value. Okay. I do not know what power x point of length, velocity and the rho will make it a non-dimensional form of pi 1, or I do not know what is the power exponent could be there to make a non-dimensional form of length, velocity, density and the dynamic viscosity to make a pi 2 will be non-dimensional number. So, now it is easy. So, you consider the power exponent for the length will be A, velocity will be the B and density will be C. It is a very easy. Now, you substitute the dimensions of the length, velocity and the density A, B, C and all multiplied with the force should be equal to dimensional less. If phi is a dimensional less, then m naught, T, L naught and T naught. If that the conditions, you just equate the power exponent of the mass the power exponent of the length, power exponent of the time, and if you equate it, you will get it this ABC value of these ones. It's very easy. If that, then you are you get a non-dimensional form of force divided by density U square by L square. L is the length square. Okay. So, if that is the condition, this is called the coefficients of the force CF. Okay, that's a different name, it's there. The same way, if you do for this pi 2, where same ABC you can consider it, it does not matter it, and mu here is the dynamic viscosity. Again, I substitute the dimensions of length, velocity and density, equate it, I will get a ABC value of that. Then I get a pi 2 this, which is a reciprocal of Reynolds number. Okay, the reciprocals of the Reynolds number. That means the one of the pi 1 is a function of a phi 2. That is what you have written it. Only we have just the reciprocal of Reynolds numbers, you make it another Reynolds number format. So, this is what our non-dimensional form. This is what is our non-dimensional form. So, similar way, let us go for what are the variable in generally in fluid flow phenomena we get it. As I told it earlier, that when we talk about the fluid flow problems, the mostly we talk about the velocity and the pressure field. Okay? That is the basic things, velocity and the pressure field. Then when you talk about that, you know it, there will be a gravity force which will be taken care by acceleration due to gravity. The length dimensions will be there. Then comes out to be mass functions will be the density will represent the mass, the viscosity will define it the flow resistance. So, other two what is very important is called the surface tensions. When you have an interface of two liquids, two fluids, you will have a surface tension. Same way as we discuss many of the times, the speed of sound also matters for us to know it, flow Mach numbers or incompressibility of the flow or compressibility of the flow. So, all total if you look at any fluid flow problems, okay, can have all the dimensions or some of those. That means, pressures, length, viscosity, surface tension, speed of the sound, acceleration due to gravity, density and the velocity. These are the prime variables. Okay. See, if you look at how many are there? 8 variables. 3 are basic variables. So, that all these 8 variables can we make a 5 independent dimensional groups. That is the concept of the fluid mechanics. Okay. So, most of the fluid flow problems, okay, nowadays you do very extensive different way, but most of the fluid flow problems we can define with these 8 variables. That means, we can group them into a 5 independent dimensional groups. So, what are they? Now, I can show you the figures. I do believe it, these figures will talk many things what I may not express with these so called limited time scales. If you look at the things, what it happens that when we have a fluid flows, different force acts and the different force dominate at different conditions. And when you do the fluid flow problems, we should find out which one is dominated one and we try to solve for the dominated case. So, that is the way we look at the fluid flow problems to solve, to find out or to judge which are the force are dominating it. Like for examples, when you have the laminar to turbulent flow like this case, okay, you can see this laminar to turbulent flow what I discussed in the first class, okay, with showing the vortex heading and all. So, these are what? These are two forces are dominated here. One is inertia forces, the momentum flux, and another is a viscous component. These two forces are dominated, and those two forces the ratio is Reynolds number. You can compute this rho VL by mu. I am just leaving you to just do that exercise, otherwise we will discuss in your assignment mode. Okay. You can compute it that the inertia force by viscous force is a the Reynolds numbers. That's what we can do it using virtual fluid bulb concepts also. So let's have that. It's a ratio between a fluid flow problems where the inertia versus viscous force. That's what the rho VL by mu is defined as the Reynolds numbers. So often we use the Reynolds numbers because the mostly we consider the inertia force by viscous force dominancy, as you can see it, the vortex on the hills. Okay, that's what we discuss a lot, how the vortex formations happens in, and very smooth, just a smoke cloud from mouth, or you can have the formations of vortex settings. All it depends upon what Reynolds numbers of the flow we have. The similar way, if you go for the next numbers, it's called Proud number. It depends on the fluid flow where your gravity force also have a dominancy as compared to the viscous force. Like for examples, if you talk about this spillway, here the viscous force are not that dominant. The gravity force works dominant in sea levels. So we can have a ratio between inertia force by gravity force. That's what is flow Proud numbers. That's what we define it. That's what is defined by this as non-dimensional form. So if you look at this is the velocity, length into g of square root, also the unit dimensions of the velocity. So it becomes non-dimensional. So how to get it, this component, I think in these basic lectures I cannot complete that web celerity concept here, but I will tell it in higher classes. If you go for postgraduates and all, or the open channel flow, definitely you know it how this square root of LGs comes as a gravity force components. The same process it happens wave cloud patterns, also it happens this wave pattern generated by a small boat. You can look at these figures. It's very interesting figures. You can see this all sort of the flow dominancy. The top lines are the flow dominancy of inertia force, that's what it drives the flow, versus the viscous force. In this case, the inertia force and the gravity force. I just repeat you, please remember these two numbers because these are very common numbers, are called Reynolds numbers and flow Proud numbers. Now if you look at other two numbers where not many times we use it, but nowadays the level of the fluid mechanics problems what we are solving it, we look at this form also. One is called where the surface tension dominancy is there. Like for example, if you look at these bubble formations, all this because of the surface tension force. So in this case, if I focusing on these bubble formations, then I should look at the Weber number which represents us a ratio between inertia force by surface tension. That's the component what we are getting. But you know it, there is a cavitation occurs when the pressure drops at certain levels. Then water vapor forms is which we discuss in the basic classes what we taught it in a lecture on a lecture 2. Okay. So what it happens is in that case we try to look at how much pressure drops which generate us the cavitation process. Pressure drops, the change in the pressures. If more the change in the pressure, there is a likelihood to have a cavitation force. Divide by these inertia forces which defined as a Euler numbers or cavitations. Euler number or cavitation, we remember it in these Euler numbers, the inertia force is in the below, okay, as compared to the other numbers. So we have a 4 numbers with us, the Reynolds numbers, the flow Proud numbers, Weber numbers and the Euler number is cavitations, which happens when you a turbine moving it. We can see that there is a chance to have the cavitation formations near this turbine bed. Okay. So, but there are the conditions where the both the things are dominants, like a surface tensions and the cavitations, which is happens. It's very interesting topic that if a bullet traveling in waters, it surface tensions as well as the pressure drops creates the cavitation process. So we can see this, the bubble formations and all these formations are also collapsing of the bubbles as the bullet travels it. It's because the inertia forces is the dominance is there, surface tension dominance is there, also there is a dominance of the pressure force drops which generate the cavitations process. That's the way there are the water vapor formations are there, and that vapors are collapsing it. You see that process, if you look, it's a very interesting process. What is happening it, just firing a bullet in water. That means two the process are happening in say dominance as with respect to the inertia forces, we have the dominance of that. Now if you look at there another two components, which is a Mach number, flow speed by the sound speed. Okay, this numbers becomes 1 when the flow speed is equal to the sound of the speed. Okay, if you look at that Mach number of Boeing 737's flight max will be the 0.785, which is a subsonic flow. Okay, but if you talk about the fighter jet of SR-11 Blackbird, the Mach number is 3.35. That means the flow velocity is much larger than the speed of this fighter jet is larger than the speed of the sound. You can understand it what way, but this is not case in case of your domestic flight, but the fighter plate smooths that. So you need a different technology and all the things. If you are really interested, just Google it and get it, what the flow field for the fighter jets and what is the flow field for the Boeing 737s. So these are the two different Mach numbers, and the flow pattern changes it. The compressibility changes it. In both the cases here, the compressibility matters, because when Mach number more than 0.3, we talk about the compressibility. So both the cases we have the flow compressibility. So that way we can know it that with respect to the Mach numbers, the flow speed and the sound speeds, okay, with aerodynamics and more advanced level you know it. So we can know it what is the range is that. And another ways you know it, as we discussed, is the drag coefficient, which is the drag force divided by this rho v square by a, which is a dynamic force. You just substitute the dimensions and you can find out is a force component when you have a rho v square into a. And why does the half is there? Please you think it. So if you have the drag force, as we said it earlier, is that today technology has developed and all, we do the modeling at the full scale levels, at the prototype levels, if you look at these things. And with a smoke or any jet, we can know exactly streamlined patterns, how it happens it at different velocity and the drag force component. So this is what is designed for a speed to moving more than 200 km per hour. That's the reasons, even if there is a cyclone, we cannot have a rolling. But what has happened to the bus? It has not designed for the 200 km per hour. So that's the reasons you can see the rolling of the bus in cyclone situations, but that will not happen in case of well designed the car what you have, because these are all designed for high speeds. The design velocity itself is close to 200 km per hour. So we will not have a ruling conditions what we have seen it. Bus is a ruling conditions when you have the cyclones. That what will be not there, because it is well tested at the prototype levels. It's not in the model level, it's a prototype levels, and to find out what is the drag force. Based on the drag force, it has designed all the components, where the weight should be there, where the lightweight will be there, whether how many passengers are sitting inside or not sitting inside, all the conditions they tested it, and to find out the best, the safe, which even if extreme design conditions of the speed of let it be 200 km per hour, still this will be the not going to be ruling conditions what we saw the ruling of a bus in cyclonic funny. Okay. So let's coming to the closures to this. Before that, let's have a 2 or 3 examples which are very easy things. I will not repeat much things. That let have a find out a independent of dimensional group using there is a Q, which is a volumetric discharge, is a functions of R radius, dynamic viscosity, and the gradient of the pressure. Okay, we have a N4, J we know the 3 mass length and time, because all these things, as soon as you write the dimensions of discharge, R, mu and dP by dx. We remember this is the dP by dx. That means find the pressure dimension, divide by the length dimensions. You will get a dP by dx dimension. So, once you know these dimensions, as you know that it will form a one independent dimensional group, we will follow the same concept. I am not going to repeat it here. Again you put a substitutes of power exponent of ABC, substitute these dimensional values and equate with non-dimensional pi value, you will get ABC value, and finally you will get the relationship between these the four, which will make a non-dimensional group. It is a very example simple things, but first thing is that we should remember the dimensions of the fluid variables. And this is another example 3, where what the basic difference is here is that we have a dimensional groups, we have to make it with a conditions which is not a fluid flow problems. Is having a variables which is a E value is there, and you have a P, you have a length, you have a deflection, something like you have a deflections. So, you have a length dimensions, you have pressures, the dimensions, you have length I, and you have a E value. In this case, what you have to look at that when you have this type of two conditions where you have a having this mass. So, we cannot make a three variable combine it make a non-dimensional. Only the two variable can consider is to make a non-dimensional form. So, our instead of 3 we are use the 2, because 3 variable we cannot combine it to make it a non-dimensional forms. So, because only these two variables here having a dimensions where the mass is there. See, in that case you will consider j equal to or r equal to 2. So, you will make a 3 independent dimensional groups from a pi theorems. That is what the difference. Now, if you look at these tables, we look at a pi 1, pi 2, pi 3 with a 2 repeating variables, okay, and 3 non-repeating variable. Substitutes all these values, solving it, getting the values A, B. Finally, we get a relationship that. So, if you are good in a solid mechanics, you can interpret it what they are. Okay, it's very easy to interpret it this part, because you can know it what they are. Okay, it is not very difficult. So, this is moment of inertia. Okay, that you can interpret it what these are the deflections values and all. So, what I am to take is that the dimensional analysis we do not do for fluid mechanics, any experiment we do this dimensional analysis to know it the relationship between dependent variables and independent variable in terms of dimensionless formats. So, with this let us have the closing these lectures. Before this, I think today what we have advantage to fly from one place to other place by aircraft, it is possible because of these two really adventurous people in the world. In early 19th century, they try to do it something just looking the nature. They had if you are really interested to know this, you just put it the Wright brothers, Google it, and you can know it what way they struggle their life, how many failure they face it before get a succeed to have a what they have succeeded. They first plane they succeeded with a 59 seconds in the air at the height of 852 feet, okay, and because of their success, okay, now we are having the aircrafts and all, because people, the human being felt it was easy for now to fly it. But what they did it, how did that success, these are not that well educated or this, but they are adventurous spirit. They used to look, they had a series of the failures. They left their country, came to other country, and in that period I will tell you that the Europe's top universities also were looking to develop something like this. Top professors are in Germany, Europe, all these countries people, they were trying to look it, but nobody has this type of advantages, what they had that. So what do you want to tell to these? When you do the experiments, you do you expect the failures, but all the failures sometimes make a success story. That's what these people prove it. And all these failures will give it us a opportunity to think, why do have the failures? One thing's what they did it, just they follow the bird's wing for the balance and the control, which is necessary to fly. Just looking this bird, if you look at that, which called wing warping, that's what they have designed here, which nobody in universities professor could do that thing. And that's what is the spirit, advisory spirits makes the world in different forms, not the basic knowledge, because you tried, you fail it, you learn it, and that learning spirits makes the things which is something what nobody has invented. So with great salute to these two brothers, and someone has a very, so with this let's conclude these lectures, and you know it, what is the dimensions, what is the dimensional homogeneity principle, and what is the dimensional groups in the fluid mechanics. We will repeat these things in the next class. With this, I thank you for your attention for this class.